Thank you. Hello again. So aside from phishing, we also have interest in sandboxes. So essentially, the whole purpose of this other research that we did is we've been investing a lot of time and effort in sandboxes, in customizing sandboxes, and from the result that we see, more often we see the malicious applications trying to evade user-land hooking. So we know, various techniques that are used by malicious actors to use things like direct syscalls, which typically will evade most open source sandboxes, things like Cuckoo or Cape v2. So with that in mind, we started thinking on how can we improve this and how can we write our own module to catch this sort of behavior. So let's start off with something that most of you have seen or started working when you started on your careers. Hello world. So this is essentially a small snippet of code which writes hello world into a file. So let's see what actually happens behind the scenes, and we'll go from there. So typically when you try to create a file, on the system side, you're going to see an API call. So in this case, we're going to see create file W. We have all these parameters, including the path where the file is going to be created. And from that point on, it's going to go through a series of other functions until it reaches ntdll create file. And from ntdll, from create file, we're actually going to see some interesting instructions, which is, in this case, move ex55h, and then we're going to see a system call, which is essentially the gateway towards the kernel space. So this is pretty much the flow for a very, let's say, typical application, starting from your code all the way through these Windows APIs, and then towards the kernel. And now Chris is going to tell us a bit about how hooking works in general, how user-land hooking works, and how this can be evaded as well.
Thank you, Mihai. Okay, so moving forward, let's consider this very simple example. We have one malicious application. We have a malware which wants to write a file on the disk, right? So at some point during its execution, it will either directly or indirectly reach the ntcreate file from the ntdll in order to basically create a file on disk. And if we want to monitor this kind of behavior, the most typical solution for this is to perform some hooking into the user space. So usually what monitoring solutions do is that they replace the first bytes from the ntcreate file in this case with a jump instruction to our hooked version of the function. We execute whatever we want, our custom logic, and then we execute the original instructions, and then jump back to the normal execution flow, right? But the problem with this approach is that instead of relying on the function call, or instead of performing the function call, malicious application can basically do a system call directly. And there are libraries out there, for instance, syswhisper, which can make this thing quite easy for an attacker to be implemented. Our proposed solution for this problem is to, instead of rely on user-land hooking, to create to have a kernel driver which would perform the hooking inside of the kernel. And by doing this, we will be able to monitor all the system calls. Now, going forward, in order to understand how to create a kernel driver to properly monitor system calls, we need to first understand what's going on behind the scenes when a system call is performed. And for this, we'll take a look at the pseudocode of the system call instruction and see what's going on behind the scenes. There are two main things which are going on. First of all, the privilege level is set to 0, such that the kernel driver will have more access to the hardware. And second, the value of the instruction pointer is set to the value of the L star register. L star register is the register which contains the generic system call handler for system calls. And if we take a closer look on a live Windows machine with a debugger, we'll see that inside the L star register, we'll find the address of the KI system call 64 function. Going forward, let's try to understand what's going on when we execute this function. So the first thing, the first decision which is made is on what kind of system call table to be used. There are two main system call tables. There's SSDT and shadow SSDT. Shadow SSDT is basically the system call table used for handling the GDI calls, while SSDT is the generic one for handling typical system calls such as integrate file. Going forward, there are a couple of checks which are performed if the system call number is in the valid range. After that, we obtain the relative address of the specific system call handler. We obtain the absolute address, and then finally perform the finally call the actual handler for integrate file in this case. And if we take a look at a running kernel with a debugger, we'll see that the entries from the SSDT table looks something like this. So as a recap, the malware basically sets the value of the EAX register to the system call number. It performs a system call. In the kernel space, the KI system call 64 is executed. It looks into the SSDT table at the offset hex 55, takes that address, computes the absolute address, and then finally call the enter create file. Now, what we are proposing is to basically modify the content of the SSDT table such that it will execute our own hooked version of the enter create file rather than the original legacy enter create file. However, there is one problem with replacing entries from the SSDT, and that is the fact that there are just 28 bits which are used in order to perform a jump. So we only have a range of about 256 megabytes of jumping around the anti-kernel. And since we don't know for sure where our kernel driver will be loaded, we need to somehow get around this restriction. And how can we do that, right? I think that you are all familiar of how a Windows application and both in kernel space and user space look like. So between actual code for functions, there is typically some padding, and in this padding you usually find some instructions. In this case, it's the int3 instruction. For the normal execution, this doesn't do anything at all. However, the purpose for this instruction is basically in case of an error, rather than go into executing some unknown code, going into some undefined behavior, we basically prefer to signal the kernel and show a blue screen instead. And what we are proposing is to basically replace the content from replace those instructions with two instructions of our own, mainly setting the value of a register and then jumping to that register. And by doing this, we are able to perform an absolute jump instead of a relative jump. Right. Going forward, there's one more problem which we need to tackle, and that is how do you know that integrate file maps to the system call number 55 hexa, right? We don't know for sure this. And this basically changes across Windows versions. The easiest way would be basically to look into some. There is some website which provides this information. It's unofficial, but it's quite good, and we can use it. And if we don't like it, we can basically perform a reverse engineer. We can do reverse engineering and extract the system call number by ourselves. However, the problem with this approach is that it requires manual intervention. We don't like this. So instead of doing that, we prefer to use a technique which is called Hell's Gate, which does the following thing. So the process executing can basically load the NTDLL file, look into the exported functions. It can look for the NT-create file and then perform some sort of a reverse engineering, automated reverse engineering, well, more like pattern matching, and extract the system call number from there. And the main advantage of doing this is that our code is no longer specific for one version of Windows, but it can work on various Windows versions. Okay, so we have pretty much every primitive which we need in order to write our kernel driver. And if we try to actually run it, we'll see that there are a couple of issues which we get into. The first one being the fact that kernel drivers need to be signed. And since we don't have a valid signing key from Microsoft, we had to basically disable the signature checking on our machine. Going forward, when we try to execute it, we get a page fault. We get a page fault for a write operation, and this is mainly due to the fact that we are trying to override some instruction, and the content of the SSDT table, those are stored in read-only and read-execute areas, and we don't have permissions, right? So we need to somehow get around this. So what can we do? Luckily for us, there are already open source projects which are doing something similar to this. One of them is ZeroMon. And what they are doing is to basically set the value of the CR0 WP register, the write protection bit. They are disabling such that any kernel code can basically write in whatever page it wants, even if the page doesn't have write permission enabled. However, if we try to execute this, we will get a privilege instruction exception. And basically, this is due to a recent enhancement coming from recent generations of Intel CPUs. So in Intel Gen 11, they introduced something called control flow enhancement technology, which basically doesn't allow us to modify the write protection bit when it is enabled. So what we did was to basically disable interrupts, disable CT, disable WP, write whatever data which we wanted into memory, and then finally re-enable them into reverse order. And by doing this, we managed to get our kernel driver running under debugger. However, on a live system, there's a security component called patch guard, which ensures that critical data structures from the kernel are not corrupted. And well, since we are trying to override the SSD values, we get a critical structure corruption error. And we managed to get around this by using a custom bootloader called EFI guard, which ensures that patch guard is never loaded during boot time.
Thank you. So in the end, this is kind of the final step. If we look back at all that that's been said and done, there's a bunch of challenges that we faced, start ranging from insufficient public documentation for various like kernel kernel APIs. There's a lot of let's say upgrades and features in Microsoft, in Windows specifically, that enable a lot of protections nowadays. And we had to jump through a lot of hoops in order to bypass those and to actually be able to write and run our own kernel driver. And in the end, so what's the outcome from this? Well, essentially, as we mentioned in the beginning, we tried to take a POC for that example of write a file and use something like syswhispers to do this with direct system calls, which would be normally hidden in a sandbox. We took that binary, ran it in some public instances of Cape v2, which is a public sandbox, open source sandbox in Cuckoo. And essentially what you're left with is you have a file that was being created, but you don't have any sort of information on how that file was created or when that file was created. So it's basically the problem that we're trying to solve. And on the lower side of the screen, this is actually some output, some logs from the kernel drive that we wrote, which essentially traces all this information. So we can see that the actual the file which was run with a PID, and then we can actually see the kernel area of for the hooked integrate file and the actual invisible file that we wrote. So at the end, essentially, what we're trying to did essentially to try to have a kernel driver that you can use in conjunction with normal sandboxes in order to get more visibility in areas that would normally be, let's say, out of reach for you. So that's kind of it for us. Thank you for attending. And if there's any questions?
Very interesting work. What was I wondering is there a way to filter out for, I don't know, valid processes? Or you just hook and print the log for all files that are being modified or written in the system?
That's a great question. So what you can do in order to filter based on processing is to, well, you have to implement your custom logic inside the kernel. You have the primitives to perform the hooking, and you will see all the logs from all the executing processes. And if you want to filter based on the process ID, you always have this option. You have all the necessary data inside the kernel. You know which process is currently executing, so you have that kind of information. The only thing which is left for the developer to do is to basically have a logic in order to decide whether or not a process should be monitored or not. Does this answer your question?
Okay, yeah, it does. And another question, inside the kernel field, can you see all the details about the process, like the parent ID or the image, or if it's from a loaded DLL or something like that? Or some information that you can track down the line to
Everything that you have in user space, you also have in kernel space. It's just more difficult to access it, but the information is there. You can use it.
Okay, so it can be done through the function that you wrote, the handler, right?
Yep.
Okay, thank you.
Just as a to add something to this, so again, what we're thinking of and how we're thinking of using this is to use them in conjunction with the user land hooking that sandboxes normally provide. So that way you can actually correlate information regarding what's the process that you want to monitor. So you basically, when you run the sandbox and detonate the binary, you know the process the process ID of your binary. So you can actually use that information and pass it along towards your kernel driver, and then you've solved that problem from the beginning. It's just more of the problem that comes afterward is when you have child processes and what you want to monitor afterwards. Thank you.